Okay, I've gotten several questions about U-substitutions. I'm going to do a couple examples for those of you that are trying to do your homework and you're confused. Okay, so let's try one, for instance, like this. So let's say I have the integral of x cubed, and then I have 1 minus x to the fourth raised to the fifth. Okay, so if I want to solve this with U substitution, I first need to decide what my U is. Okay, and this is very similar to the chain rule. Oftentimes it's the part that's inside, like the chain rule. So we're going to let U equal 1 minus x to the fourth. And then du, which typically we write as du over dx, the derivative of U in terms of x, is negative 4x to the third. Okay, but instead of writing that, it's kind of like, you know how du over dx is often units, like meters per second or something like that. We can multiply the units over. So instead of having the dx here, you could actually think of it as being over here. That's really the easiest way to think about this. Okay, so when I look at my various parts, I realize that this part right here has been replaced. It can be replaced with u to the fifth, right? But I still have x cubed dx left. Okay, so if I can somehow solve for that portion and put it in, then I'm good. So I notice that I have x cubed dx here, so I'm just going to divide by that negative 1/4, or negative 4, and I'm going to have negative 1/4 du, oops, that's a bad u, equals x cubed dx. Okay, so then I substitute, and I say, oh, well, my x cubed dx, which was underlined in blue before, is now replaced with negative 1/4 du. Okay, so I rewrite. So I now have a new integral that's all in terms of u, and it looks like negative 1/4, which I often write in front. So I'm going to do that there. Oops. So I have negative 1/4, and then I have my u to the fifth. Ugh, u to the fifth du. My stylus is terrible. My son destroyed it this weekend. Okay, so I have negative 1/4, and then I'm going to have, when I integrate, I get u to the sixth with a 1/6 out front. And of course, plus c. So my answer is negative 1 over 24, and it was u to the sixth, but remember, u is 1 minus x to the fourth. So I have 1 minus x to the fourth to the sixth, and then plus c. And that is your answer. Now don't do anything crazy. Don't try to bring the sixth power inside or anything and say it's 1 minus x to the 24th, because you can't do that. Remember, if you were going to multiply all of this out, you would have to actually FOIL it out 6 times. Okay, so don't try to bring the 6 in or anything crazy. Okay, so let's try another one. Okay, so let's say I have something a little bit more complicated, maybe something where you don't have exactly what you want with your substitution. Let me see. So how about something like this? So what if you had x plus 1 on top, and then you have x squared plus 2x on bottom. Okay, so dx. Okay, so if I was trying to integrate that, I would need to first decide what I'm going to let my u. Now, oftentimes, like I said, the u is pretty obvious. It's going to be something kind of like the chain rule that would have been in parentheses, squared or whatever. Okay, but on this one, it's not as obvious. Okay, this one, it's a denominator. So we're going to let our u equal x squared plus 2x. Okay, and then du is going to be 2x plus 2. And remember, it's like I had a dx on the bottom on the other side, so I'm going to multiply it over dx. So when I look at this, I do recognize that the bottom is u. So when I replace, I have over u, but then I have my dx. Okay, so this is the type of situation where it might be handy for you to do another method, and I talked about this a little bit in class, where you can actually isolate the dx. So you have du over 2x plus 2 equals dx, and then you replace everything. So up here you'd have still the x plus 1, and now the dx is being replaced by du over 2x plus 2. And when you do that, hopefully you guys are good enough with your algebra skills that you realize x plus 1 and 2x plus 2, if they were like one over the other. So let me write it over here. So x plus 1 over 2x plus 2 is really 2 times x plus 1, right? That's what 2x plus 2 is. So then your x plus 1 over x plus 1 reduces down, and you get 1/2. So you have 1/2, and then you have the 1 over u and the du. Now, personally, I don't like this method. I like to see what I'm going to replace at this step right here. So what I probably would have done, and what I'm going to do in class, is I don't do the thing where I solve for dx, which is fine. If you like that, go for it. But when you have these more complicated ones, so something a lot more complicated than this, it's just a lot of writing. So what I typically will do is I'll notice that if I pull out a 2, I have x plus 1, which is what I need. Like I would see I have x plus 1 and a dx. And I'd realize that I need to divide by 2. So I have 1/2 du replacing the x plus 1 dx. Okay, so then I go straight to this step. Okay, so it's up to you. If you like one method, then do it. If you don't like the other one, that's fine. So we're going to have 1/2, and then we have the integral of 1 over u du. Okay. So 1 over u, if you think of it as u to the negative 1, and then you try to integrate with the power rule, you would have u to the 0, right, when you add 1 to the power. So it's something special. So 1 over u is actually, when you integrate it, you get natural log, right, natural log of u. But we go a step further. We always do natural log of the absolute value of u, because we know we can't take the natural log of a negative number. So it just ensures that we don't have that. Then we still have the 1/2. So your answer is going to be 1/2 natural log of u, which was x squared plus 2x, plus c. And that's your answer. Now always be on the lookout for weird things, though. On your AP test, I mean, they could do crazy things with natural log answers. So when you see something like x squared plus 2x, just recognize that you could have, let me kind of give myself some room here. You could have x times x plus 2. So on your AP test, they may write it as natural log of x plus natural log of x plus 2, because they're crazy and they do things like that. So just recognize that that may happen. Okay, so let's try another one. Okay, so let's try maybe something with like sine, cosine, something. So how about if I do something weird, like the square root of cotangent of x, and then I have cosecant squared x dx. Okay, you can always rearrange. You can always move things around, like with sine and cosine. So you could rewrite this one as 1 over sine and then times itself, so squared. And then you can rewrite the cotangent as cosine of x over sine of x. Okay, but you actually don't need to go that complicated if you remember the things that I gave you in your derivatives drills. So you guys remember that if you take the derivative of cotangent of x, you get negative cosecant squared x. Okay, we're going to use that. So if I let my u be the cotangent of x, which makes sense because it's under a square root, so it's kind of the weird part, right, the chain rule part, the du is going to be negative cosecant squared x dx, which means you would have negative du is equaling this part, the cosecant squared x dx. So we've replaced everything that we want. So this part is replaced by negative du, and this part is replaced by the square root of u. So we get negative, you can pull it on the outside, square root of u du. So remember that's negative u to the 1/2 du, which means we have negative, and I add 1 to the power, so 3 over 2. 1 over that new power, so 1 divided by 3 over 2 is 2/3, plus c. So it's negative 2/3. U was cotangent, so I'm going to have cotangent of x raised to the 3 over 2 plus c. And remember, a 3 over 2 power means you could have, like if I was going to rewrite this, it could look like cotangent of x with the 3 there and then a square root, right? So raise the 3 and then under its square root. So look for strange things like that. All right, maybe one more. Okay, so let's do one where we have, I don't know, like where du doesn't replace everything that you need it to replace. So let's say I have the square root of x plus 4, but then I have x plus 3 out front. Okay, the u is exactly what you should think it should be. So your u is going to be the x plus 4, the part under the square root. And we do that because now this becomes square root of u, or u to the 1/2. You can now write it with a power. Whereas before, if you had x plus 4 quantity, like raise the 1/2, right? If you were taking the derivative, it would involve a chain rule. So same thing with the antiderivative. You would still need to do like the opposite of the chain rule, which is U-substitution. Okay, so I'm going to have du equals dx. So I'm at least replacing that dx with du, but then I'm stuck because I'm left with the x plus 3, and it seemingly, like, at first it doesn't seem like it has anything to do with u. Okay, but it does. Because if you notice, you can always solve for x. So if I solve for x, I would get x equals u minus 4. Then I go in here and I replace. So I have u minus 4, that was the x part, but then I still had plus 3, right? That was replacing the entire x plus 3. And then I have the square root of u, which we said was u to the 1/2, and then du. And it still looks overly complicated, but if you notice, this is u minus 1 times u to the 1/2, which actually works out really nice because now I have u to the, right, this was u to the 1, so add your powers, u to the 3 over 2, and then minus u to the 1/2. And then I can integrate from there. So I would get u to the 5 over 2 with the 2/5 out front, and then minus u to the 3 over 2 with the 2/3 out front, and then plus c. So your final answer, give myself some more room here, should be 2/5. U is x plus 4, so x plus 4 to the 5 over 2, which again, this bottom number is a root, so you could have a square root in there, so all of it raised to the 5, but then all under a square root. And then minus 2/3 u, so x plus 4 to the 3 over 2, plus c, and that's your answer. Okay, and then the last ones that we had were the strange ones that kind of involve like secant and tangent. So let's look at one like that. Okay, the last one I want to show you is something like if you have secant cubed x and then tangent x dx. Okay, and the ones that involve secant and tangent, and also sine and cosine, can be a little bit tricky because it's often hard to figure out what you should let your u. So let's say I went ahead and I tried u was equal to tangent of x. If I did that, then my derivative of u would be secant squared x dx. So when I replace, this part would be my u, the tangent x would be u, but then only secant squared, right, would be replaced. I'd still have an additional secant x there. So that actually will not work. So I can't do that. So I'm going to need to try something else. So what if I have secant cubed x tangent x, and instead of letting it be tangent, let's say I let u be just plain secant. And notice I'm not doing like secant squared or secant cubed or anything like that. I'm just trying just plain secant. Because then the derivative of u is very straightforward. You should all know this from your derivatives drills. And it's secant x tangent x. And we tack on the dx. So when I replace, it's helpful to think of this in expanded form. It's secant x times itself 3 times, and then a tangent x dx. Okay, so all of this is being replaced with the du. And this involves u. So do you see how it's u times u? So when we replace, it's actually only u squared. It's not u cubed because one of those secants had to be used for the derivative. So it's u squared and then du. So then we integrate and we get u cubed with a 1/3 plus c. So it's 1/3 secant x cubed, or you could bring the 3 in between the secant and the x, plus c, and that's your answer.